Hi everyone, my name is Jati Bowo. It is my pleasure to present my work in the 21st of ISITIA. I will present my work titled Distributed Observer Approach for Scalable Formation Control of Multi-Agent Network. My co-author is Muhammad Roshan Fikri, and we come from Sampurna University. This is the outline of my presentation. I will begin with the introduction. Multi-agent formation is an active area in the cooperative control of multi-agent systems. Scalability is an important feature in multi-agent formation. This shows the illustration of scalable formation. Scalability allows for adaptability of the group to the change in mission and environmental condition as shown in the illustration. Past works on distributed scalable formation consider undirected network and directed network with k-rooted graph, whereas this work considers directed network setting where spanning tree is necessary and sufficient condition. Graph is used to model the interaction network among agents, and these are the standard notation of graph that is used in this work. L is the Laplacian matrix, and we also use the standard notation of spanning tree condition. We consider n single integrators agents given by equation 1. xi in equation 1 is the position of agent I, and ui is the control input of agent I. The objective is stated here. If we let xid for all I to be desired position of agent I on the local coordinate system, then the objective is to design the ui in equation 1 such that for any initial states for all I, we have equation 2 to be satisfied. Ct0 in equation 2 is the scaling factor of the formation that depends on the initial starting time t0. Equation 2 means that asymptotically, the relative position between any two agents are equal to the relative desired position multiplied by a scaling factor Ct0. Now we come to the main result of this work. The proposed control input are given by equation 3. 3a is the control input and the 3b is the estimator. xi hat is the estimate of xi, and we see that from equation 3a, only the relative position of agents is needed in the control input. If we let x and x hat be the vector, the overall system can be expressed as equation 4. We have L as the Laplacian matrix, phi is the self loop Laplacian associated with graph G and formation factor xd, with phi I equal to xi and phi ij equal to minus aij. And R is a diagonal matrix where the element of Ri and Si is given by 5 and 6. This is the main result also, and we need this lemma to show the main theorem. This lemma shows the spectral properties of the matrix phi. So we have 0 to be the eigenvalue of phi with eigenfactor of xd. And also if we let xid greater than 0 for all I, we have that the non-zero eigenvalues of phi to be positive real part. And 0 is the simple eigenvalue of phi if and only if G contains a spanning tree. So this is exactly the same spectral properties as the Laplacian matrix, except that the right eigenfactor of phi is the formation factor xd. And this is the main theorem of this work. If we consider system 1 with the control input and estimator given by equation 3, and we suppose xid is greater than 0 for all I, then the objective of the scalable formation holds if and only if graph G contains a spanning tree. The formation scaling factor can be defined as follows. So from the main theorem, we know that the limit as t goes to infinity of xt is cit0 times xd plus c2 of t0 times 1n. 1n is a factor of all I. of all 1. C2T0 is the common bias term that applies for all agents, while C1T0 is the formation scaling factor, and it is bound to be Y phi transpose X hat T0, and this is also the formation scaling factor CT0 that we defined earlier. And Y phi transpose phi equal to 0 holds, so it means that Y phi transpose is the left eigenvector of the phi correspond to the 0 eigenvalue of phi. We know from here that the formation scaling factor depends on the graph topology and also the initial state of the estimator. Without loss of generality, suppose G is leader-follower graph with node N as leader node, then we know that Y phi transpose to be given here. And so, we know that the formation scaling factor is equal to the Xn hat T0, or that only agent N can affect the formation scaling factor. The numerical example is now discussed. Now we have a leaderless agent in the numerical example. The xdx and xdy are the desired formation factor in x-axis and y-axis respectively. And this is the graph configuration of the numerical example. And this is the trajectories of agents. The left and right figure shows agents' trajectory when they have different initial position. And we see that agents form a rectangular formation with different formation scaling factor. And this is the second example where we use leader-follower network. The desired formation scaling factor are the desired formation pattern are similar to the previous example, but now we change the formation scaling factor in the middle of the simulation. And this is the graph configuration for the numerical example 2, and we set agent 4 to be the later agent. And we see here the agent's trajectories. Agent form a square formation, and the first formation has alpha equal to 1, or the formation scaling factor equal to 1, and the second formation scaling factor is 2, and this is done by changing the initial states of the estimator for agent 4. Now we come to the conclusions of this work. A new method of distributed formation scaling for single integrator agents under the data network is presented. The spanning tree condition is shown to be necessary and sufficient condition for scalable formation. Possible future research directions include moving in scalable formation, which is illustrated here, and extension of the Self Loop Laplacian method to double integrator agents and linear agent model. Thank you very much for your attention.